Hello, everyone. Thank you for this opportunity to present our work on detecting ChatGPT-generated text with the Gzip-KNN approach, which we call a node training low resource approach. This is the work done with our master's student, Matthias Berchtold, and my colleagues Davide, Daniele, and Omran. We are all from SUPSI, which is like applied university. Applied Sciences and Arts University in southern Switzerland, but we come from the different institutes. So mine is ICNLSP, Dalle, Molle for artificial intelligence, and they are in the ISIN. Okay, so what is the motivation for this work? Well, yeah, as we all know, large language models are omnipresent and continuously improving. And that is giving us the possibility of having seemingly perfect texts, right, which are authored by these large language models. And unfortunately, some recent studies are showing that distinguishing the authorship of the text is very difficult even for the adults. And this, of course, is bringing the proliferation of AI-generated text and to the growing concerns about the authenticity of the text and the reliability of the content, because there is a huge potential of misuse and fraud. And as you can imagine, there has been a lot of related work already on this topic, starting from some, let's say, simpler approaches, which are based on the statistical properties and linguistic features, going all the way to the application of pre-trained language models, either without or with fine-tuning, and also using, let's say, more sophisticated methods, although that, yeah, well, it's questionable whether we can actually call zero and one-shot prompting techniques as more sophisticated, but actually definitely relying on different LLMs and playing with different LLM-based detection techniques. So you would ask, okay, if there is so much work, why do we need to do more? The problem is not solved because these proposed methods, they may achieve the desired predictive performance, both in and out of domain data. However, they typically have demanding computational requirements and memory footprint. I mean, you can imagine if you're using another LLM for detecting AI-generated content, and if you are fine-tuning it, that's very carbon expensive. So that is the substantial obstacle to their deployment, and instead we were thinking of applying a method which has been proposed last year, which is called Gzip-KNN, as a lightweighted and resource-efficient alternative to complex solutions. And so we were thinking of applying this approach to perform this classification, so identification whether the text is authored by a human or by a machine without prior training. So that's the emphasis here. So what is this approach actually about? This approach is based on three major things. One is, as you can see in the name of it, there is gzip, so there is a compression of the text which has been done. Then the distance between the compressed text has been calculated in a particular way, as you can see here. This normalized compression distance is used to identify the let's say the amount of the shared information between the compressed text. And then finally there is the step, also as it is in the name of the method, which is simply based on KNN, so K nearest neighbors, where basically we are deciding on the label based on the neighboring documents. However, there is a huge hypothesis here, and this hypothesis is basically that texts that are belonging to the same class, in this case, those who are written by humans or those who are generated by AI, that texts belonging to the same class share a greater degree of common information as compared to the texts from distinct classes. And this basically, based on this assumption, we are trying to discriminate between the two classes based on basically normalized compression distance that we are obtaining. So basically, in very fast how it works, we are compressing a text, and then for each sample in the training data set, we compress that sample and we compute the normalized compression distance between these two compressed versions. But as you can see here, okay, sorry, the notation is a bit, notation is a bit different, but basically, so we have the T and S, and then once we are compressing them together, and in other cases, we are compressing them separately, and then we are calculating this normalized compression distance. And once all these distances are calculated, we can use the distance as a measure to identify k-nearest neighbors, and basically then we just apply majority voting. So as you can see, the principle is very simple. Of course, as with every method, we can think of what are the pros and the cons of this method. As you can see, there are no tunable parameters, which makes this training lightweighted and straightforward. Actually, there is no real training, right? In a sense, how we can imagine training a machine learning model. However, there is a big disadvantage. So this, let's say, commodity that we are not actually doing a real training, and that we don't have tunable parameters, we are paying on the other side, because classifying a text sample requires repeating the concatenation between this text sample and all the samples from the training set, and that might result in the high inference time. So I'm basically referring to this part here, right? Because we cannot just rely on what we have obtained from the compression parts and reuse them. We have to first do the concatenation and then do the compression, which is why we have this huge inference time. Nevertheless, we were asking ourselves, can we actually use this method? And with that regard, we defined several research questions. So first research question is, to what extent can this method actually detect AI-generated text? Okay, we used ChatGPT in this case also because ChatGPT made, let's say, this world to LLMs more publicly exposed. And also a lot of studies are actually focusing on detecting ChatGPT-generated text. So that's the question. Can it actually be well performant to discriminate between the classes? And can it also outperform traditional machine learning supervised approaches in terms of predictive performance? So that's our first research question. In our second research question, we wanted to compare Gzip-KNN to the other approaches, this time not in terms of predictive performance, but in terms of training time and inference time. So in a way, complexity, but time complexity. And as a third question, we wanted to see if this method can outperform traditional machine learning approaches in the out-of-domain context. So basically, when training is done on one type of data set and the testing is done, inference is done on completely, evaluation is done in something completely different. And also we wanted to discriminate in this case between two different cases when we have data constrained and inference time constrained scenarios. What we used as data are 5 different data sets, and as you can see, we carefully selected them from different domains. So 2 of them encompass various topics, while one is IT, so information technology specific, one is finance specific, and one is medicine specific. This is also because we are testing this out of domain scenarios, right? So we wanted to see how well it can really discriminate between different domains. And here you can see we basically choose to have a balanced scenario to avoid at least imbalanceness problems. So we choose these data sets which are already freely available, which have open-ended questions, which contain both human and ChatGPT responses to a set of queries. And then this was the number of the answers that we selected per each of the class, so per human and per AI-generated texts, and the references from which papers we have collected this. So given our research questions, we had two experiments. And in one experiment, we were assessing performance versus complexity. And here complexity is actually stands for inference and training time. So this is related to the research questions 1 and 2. And in the second experiment, we actually focused more on out-of-domain context to answer our research question 3. So for the experimental setup, yeah, maybe in the interest of time, I will not even go in many details. Maybe the most important thing to say is that we used 5-fold cross-validation, and we considered 3 different models: logistic regression, extreme gradient boosting, and gated recurrent unit. And then, of course, we had performance evaluation metrics, accuracy and F1 score, and we had complexity, which is, as I said, mostly training and inference time related. And then in the out-of-domain context, we had out-of-domain context experiment, which is our second experiment, which answers research question 3. We had 2 different scenarios. One where we posed constraint on the amount of the training data available, and the second, which was constrained on the inference time. This is also because you will see as the outcome of the first experiment what were the conclusions. So I hope everything will set well. So basically, as the result of the first experiment, when we were looking the performance, here you can see accuracy, and here you can see weighted F1 score for all 4 methods. So logistic regression in blue, XGBoost in orange, gated recurrent unit in green, and Gzip and KNN in red. And as you can see, here we have also on the x-axis the various ranges of the training data set. And you can see that we ranged this from 100 to 5,000 sample size. So you can see that for a very small training set, like 100 samples, Gzip-KNN outperforms the competitors with quite a high performance gap. And you can also see that as the dataset size increases, this performance gap between Gzip-KNN and the competitors is actually getting lower and lower, so it decreases. And you can actually also see that Gzip-KNN performance gets saturated somewhere around 0.89 at 5,000 samples, training samples, which kind of means that it has a very good performance if we have a limited training data set size. But then eventually it gets outperformed as the training set size increases. But we can see that even for a smaller training set, it kind of discerns well the main characteristics, and it is capable of discriminating between the different classes. What concerns the training and inference time results, here we can see that for the training time, and these are the results in the second for different training set observations sizes. Sorry, so this is again the same scenario from 100 to 5,000 samples. So these are averaged over 10 different evaluations. And as you can see, Gzip-KNN is doing great on the training part, where it has this slightly increasing trend, but actually the training times are exceptionally small. So it
Sorry,
demonstrates.
Sandra, we have to wrap up slowly.
Okay, yeah. So you can see that for the training time, it performs great, but for the inference time, it actually has a very bad, let's say, performance because it exhibits relatively higher inference times compared to competitors. When we look at the out-of-domain context, we can see that it's comparably good to the other data sets. So these are the test data sets for different domains. But you can see that for example, OpenQA, it performs the best, both in terms of accuracy and F1 score. When we are limiting inference time, we are seeing that it outperforms again competitors on the OpenQA dataset, while on the others it's somewhere there, but actually it gets also outperformed by competitors, especially on the medicine dataset. So to conclude, we have evaluated the effectiveness of Gzip-KNN method in the task of detection of ChatGPT-generated text. We compared it with Logistic Regression, XGBoost, and GRU in terms of classification, performance, and model complexity. What we can see is that it outperformed the alternatives in terms of classification performance when we have limited number of training samples. It also yields remarkably low training time. But what concerns inference time, it has significantly higher inference time. On the out-of-domain settings, it yields comparable classification performance while utilizing only a significantly lower amount of training data. And for the future direction, we would like to look at the compression and distance calculation mechanisms, and we would like to try to optimize the interplay between these two components to extract more nuanced information and potentially push its performance boundaries, because we saw that it was getting saturated, so we would like to go beyond. Thank you very much for your attention, and if there are some questions, I would be glad to take them.